What is a computer? What do we need computers to do? Why are they useful? What are they good at? Math, calculations. They're good at calculations. Yes, that's pretty much it, in fact. So calculations, doing math. So what kind of math? We talk about add and subtract. We're going to skip multiply and divide for right now, just to keep my life easier. What else do we use computers for? Logic. And, or, XOR maybe. Not. We talked about not and XOR are related to each other. All of this is done in a computer by a special combinational circuit called a arithmetic logic unit, or ALU. We draw it like this. I'm not very good at drawing them, so bear with me. Looks kind of like a funky sort of home base with this like, there we go. That's kind of what you'll, the diagram depiction of an ALU looks something like that. ALU has two inputs. These inputs are buses. A bus is simply a collection of wires. They're usually ordered. And we're talking about 32-bit architecture, so we're just going to focus on 32-bit arithmetic, 32-bit operations. So each of these buses is 32 bits wide. Arithmetic logic operations other than multiply on 32-bit inputs is a 32-bit output, and that's all we're going to have as well, is a 32-bit output. We need something to tell the ALU what to do. We'll put that here for right now. And it's got to be a multi-bit signal because we want our ALU to do more than one or even two things, right? So how wide will this be depends on how much stuff this ALU's got to do. Okay, cool. Actually, I want more contrast. Why do I want more contrast? This thing is in control of this thing. This is telling the ALU what to do. And so I made it green. Things that are telling other things what to do, I'm going to make green. Separate these two concepts. The two concepts have a name: control and data path. The path down which data goes. Cool. We have an ALU. We can do the stuff a computer has got to do. What is a computer? A machine consisting of processor, memory, and I/O that executes a program. Well, the program tells the computer what to do. What is a program? A sequence of instructions and data. What part of the program tells the machine what to do? The instructions. What is an instruction? Operation and operands. The operation of the instruction tells the processor what to do. How do we get the operation of an instruction from a program to here to tell the processor what to do? If you told me this is what the processor does, this is the important thing. How do we get to here? Where do we begin? Where does the operation come from? The program. Where is the program? Memory. Specifically, we're going to have instruction memory. Programs in here somewhere. How do we know where in the instruction memory to get an instruction of the program we want to execute? Program counter. What is the program counter? A register. What is a register? Actually, I showed you what a register was, so you know it's in our digital logic discussion. So I'm going to put it here. The program counter. It's a register. What is a register? Well, a register is an array of D latches. We talked about those. Reach way back before Labor Day. D latches. Remember what a D latch is? If not, go back and review. Slides, videos are posted. D latch is sequential circuit, which means it's clocked. There we go. Hey, look at that. It's going to change on, let's just say, the rising edge of the clock. Every rising edge of the clock is going to allow my program counter to update and therefore advance through the program. So this is how we're going to fetch instructions in the program and how we're going to change which instructions we fetch by tying changes of this program counter to events associated with the clock. Program counter is a register. For now, we're going to call it a 32-bit register, specifying a 32-bit address in this instruction memory. Whoop. There it goes to the read port of the instruction memory, or the address port of the instruction memory, telling the instruction memory the address from which to fetch the next instruction, or sometimes the next bunch of instructions, but we can ignore that. Which means out of this thing, we're going to have a read bus. Out of this thing is going to come our 32-bit instruction word for RISC-V, I31 down to 0. So I'm going to write it. So that's 32-bit instruction, machine instruction, bit 0 over here, bit 31 over here. They can't see it. Sorry, guys and gals, whoever all's on there. So that's how we read the instruction. I kind of wish this was closer to this now. I need some more space. We're going to run out of space. That's okay. Okay, cool, cool. So now what? We fetched the instruction. Any idea what we do after we fetch? Decode it. Fetch, decode, execute. Fetch, decode, execute. All right, this is fetch. There's space here for decode. What does decode mean? Undo and encoding. The instruction is encoded in 32 bits. We talked about instruction formats. We got to unpack, decode, split these bits apart to figure out what is the operation of this instruction and what are its operands. Well, how do we do that? You know, this is just 32 wires. We just split the wires apart. And we send them different places where we have logic to figure out what the heck's going on. Well, gosh, let's start with the obvious thing. What's the operation? Remember what tells us the operation? The opcode. In RISC-V, that's down here. Now I'm going to work off memory, and I'm going to get some things wrong. Specific details, but mostly right. The opcode is least significant 7 bits of the instruction. So we're going to send the opcode 6 down to 0. That's this byte. That's the opcode. We're going to send that somewhere. Some piece of logic conveniently named control. The control logic here is the brains of the operation. And this control logic is going to generate a whole bunch of outputs to send to other parts of the processor to control the processor, to control what to do. Now, one of these outputs is actually going to come down here and go into something here called the ALU control. This is actually a 2-bit control signal that's taking the opcode and sending it to the ALU control. And that's because we need to make decisions about what the ALU should do with more fields of the instruction than just the opcode. You remember we talked about func3 and func7? So we need the func3 field. It's 12, 13, and 14. How are we going to get that? Well, we're just gonna take those 3 wires. We're going to splice them. Take a wire and connect it to another wire, and now you can send the wire 2 places. That's all we're doing here. Now you can do that when you're sending wires 2 different places. You can't do that when you're receiving wires from one place, because then you'll overload your signal where you're receiving it. It's going to come back on us later. So I'm just going to take this down here and send it here. Specifically, these, and actually I need some of the upper bits from the func7 as well. But off the top of my head, I think it's just instruction bits 30 and 14 down to 12 that we send over to the ALU control, which is going to take that as input along with the 2-bit ALU op signal from this control logic to figure out what the ALU should do. So we're ultimately taking 7 plus 3 plus 7, 17 bits in the extreme case of information and condensing it down to 4 bits to tell the ALU what to do. And that's why we split it apart, so that we can make our decision better and reduce the complexity of the ALU by condensing our decision down to 4 bits, rather than telling the ALU 2 to the 17th different numbers. So now it only needs to know 16 different possibilities. You don't have to know why, you just have to believe me. Right, now we know what the operation is, and we can tell the ALU what to do. What's the other part of an instruction? The operands. In RISC architectures, in most RISC architectures, the operands for the ALU are either registers or immediates, not memory. That's going to simplify our hardware immensely. So the operands coming into here are 32-bit values that are either coming from registers or they're coming from an immediate. Remember what an immediate is? It's part of an instruction. Right? So an I-format instruction, the upper 12 bits are the immediate. Okay, let's deal with the registers first. So our format register to register instructions. We have to, how do we know which registers to read from in order to get their values to the ALU? The operands, how are they encoded in the instruction? They're index numbers, encoded as a 5-bit unsigned integer. With 5 bits, you can go 0 to 31. So we can represent all the 32 general purpose registers of our instruction set architecture. So we've got our RS and RT fields and our RD field for where we're going to end up writing the result when we're done. Let's see, RS is here, RT is here, and RD is here in the R format instruction. We'll have to eventually know these very, very closely and near and dear. We'll probably memorize them. But if not, we have the green sheet we can refer to it. It's got our instruction encodings in it. RD is 7 to 11. Well, that's going to be easy to remember. RS is 15 through 19, and RT is 20 to 24. If you don't remember them, well, he's got the green sheet right there, and you can find them, right? So RS and RT are going to tell us in an R format instructions the 2 registers that we're going to read from. I need to take the RS bits, it's 19 down to 15, and I got to send them to the register file. So this will be my registers, or my register file. The general purpose register file. What is that? Well, that's an array of registers. If a register is an array of D latches, I guess that makes it a matrix of D latches. So this will be my read reg 1 port, and I need a read reg 2 for the other register, and that's just the instruction bits 24 down to 20. And that goes into my read reg 2. And out the other side, I'll get register 1 value and register 2 value, 32-bit values that I read out of the register file. Now, later on, I'm going to need to know where to write the value, the result of the operation. So I know I'm going to need it in the register file. This is my write port, and I'm going to put my destination 11 down to 7 to the right port or the right address, the right index. That's the register I'm going to write to if this instruction writes to a register. We will go this here. That's questions. And that'll be our write data. The only thing is, not every instruction is going to write to the register file, which means we wouldn't want to, and the register file is part of the state of the processor. The register file is really an important piece of the context of the execution of your program. So your program or process context. Process is a program that's in execution. The register file and the value of the program counter are 2 very important pieces of where in the program your execution is, because it reflects what you've done so far and where you are, which determines where you'll go. Context, right? Context clues, context where you are, gives you ideas about where you are from other things around you. Register file, program counter, important context. By the way, register file is also clocked, right? The registers are clocked components. So the clock is coming here. There's also a clock coming here. to control when you write to the register file. But we're going to double clock our register file, meaning we're going to pump it on both edges, rising and falling edges. Well, we're going to hook it up to both edges. We're going to end up ignoring one of the edges, but it's not important. So we can control when we write to the register file. We only want to write at the clock edge when we're ready to write. We also have to decide if this instruction actually writes to the register file. Well, the control logic is going to tell us that. So we got this reg write control signal, Boolean, true or false. True, we write, false, we don't write. If the opcode of this instruction indicates it's an instruction that should write to the register file, then this is true. If this instruction is one that should not write to the register file, this is false, so that we don't accidentally change the contents of the register file with any kind of random garbage, which would mess up the context of our program. As programmers, we rely on a register file to only reflect what we've explicitly put in there. Well, we also need to deal with arithmetic logic operations on immediate values. Now, for the I format instructions, we're going to take one value from the register file, one value from the immediate. Remember, the immediate comes from here, the 12-bit immediate. I is an unfortunate instruction. All right, immediate. 12-bit immediate. Is that 12 bits? 20 through 31? Sure is. Different instruction sets, by the way, have different kinds of ways they encode immediates and different sizes of immediates you can use. There's no hard and fast rules here. Okay, so the immediate is here in the instruction. We need to get it over here to the ALU. We're also going to use RS. Well, RS is coming here. So we got this one hooked up. That's great for our I format instructions. But we need to somehow hook the immediate up to here. So we're going to do that here. We're going to take our immediate here. And actually, we're just going to take our entire instruction here for reasons that may come clear later. All 32 bits of our instruction here, we're going to pass it through some logic, which we're going to call immediate generation. Generates the immediate. IMM GEN. The immediate generation has access to the opcode potentially if it needs it. It has access to the func codes potentially if it needs it. Most importantly, it has access to all the immediates and all the different places that those immediates are found in all the different instruction formats. This is where all of kind of the detangling of where immediates are located in different parts of the instruction happens for all the different instruction formats. Right? Load upper immediate has 20-bit immediate. Jump and link instruction also has a 20-bit immediate, but it's in a different, it's packed in a different order than load upper immediate, for example. So this logic takes care of that. And out the other side, we're going to get a 32-bit immediate value. For our signed arithmetic operations, signed versus unsigned, right? Signed arithmetic logic operations. What we get out of here is the signed extension of the 12-bit immediate. This thing right here is going to figure out, okay, this is a signed arithmetic operation. Therefore, I need to sign extend these 12 bits. For other instructions, it's going to do something else, but we don't need to worry about them quite yet. All right. Remember what I told you earlier? Can't do that. We can't bring two signals, two wires together from two different places that are carrying different loads, different values. Really, this one is kind of junk. It's actually carrying the register value associated with 5 bits of the immediate. That's what this is. So this is garbage for the intents of this instruction. So if we combine garbage with something, we get garbage. That's how garbage works. So instead of combining, we have to make a choice. We have to select one of these two to pass through to the ALU. To do that, we use a multiplexer. We talked about multiplexer before. Handy little tool. Multiplexer is going to decide which of the two inputs becomes the output, and therefore becomes the input to the ALU. Who's going to make that decision? Well, the control logic. It knows. It knows whether this is an immediate operation or an R format or something else. So it knows whether to use the immediate, whatever that immediate is, or the value out of the second register. So that control logic makes that decision. ALU source ALU op. And these are just arbitrary names they've been given, but they're in the book, I think. So, okay, we can do arithmetic and logic. We can do it with registers, or we can do it with immediates. What else do we need to have a functional computer? Computer does calculations. We gotta have a way to keep track of what we're calculating. We need data memory. And in a RISC architecture, also known as a load store architecture, we move that data in and out of our processor, and then we calculate on our registers. So we only have instructions to load data into the processor from the memory, and to store data from the processor or from a register, store data from a register back out to memory. So we need to add support for our load and store operations. Well, what do we need for load and store operations? We need a way to get, for let's say, store. We need a way to have the value we're going to store from the register, and then the address, the memory operand, where we're going to store it. So we got to calculate the address. The address is encoded in the instruction as a base register and an immediate, which actually uses this field and some of that field, right? The S format. That's one of the funky ones where this RD is actually part of the immediate. It doesn't really matter where the immediate is, because this immediate generation thing is going to figure that out for us. So we're going to get the sign extended offset of the immediate coming out here. And we're going to want to add that to the base register. Well, we've already got sign extended immediate going into this ALU. We've got a register value going into this ALU. So all we need to do is make sure this RS is our base register, which it is in the instruction encoding. So great. The base register is here. We get our immediate. So we know that's where the ALU result is the address where we want to store the value to. So we're going to take the sign extended immediate, the register value, and we're going to add them together. Is our address, data memory, address. Now for a store instruction, what are we going to store? Well, we're going to store the value coming out of the RT register that's here. Now that value died here at this mux. It didn't get selected to go to the ALU because we selected the immediate. So that wire is dead, but 8 a.m. That's it. This is our read data 2 and read 1. So the register value associated with the RT bits of the instruction go here to data in. The address goes here. So we can read from the register file, store the value to memory, but we don't want to do that on every single instruction. We need a control signal to tell the memory, this is a store instruction, and you should store the value you see here at the address you see here. That's easy enough. So there's our write enable signal, memwrite. Going into the data memory, controlling whether or not the memory is going to write the value it sees here to the address it sees here, which is only going to be asserted. It's only going to be a true signal when it's a store instruction, because those are the only instructions that we're going to store the memory on. Probably forever in this class. So we got memwrite, store instruction. Load instruction is very similar. Load instruction uses the I format, load word to a register from a memory address. The memory operand is going to be constructed the same way. RS is the base register. The immediate gets added to it to give us the address. We're going to tell our memory where to load from. What happens here we don't care about, because we're not going to write this value. We're going to have memwrite is going to be 0. It's going to be false. We're not going to write to memory. We're going to send a different control signal to the memory to tell it to read. We're going to send it a memory signal. Strictly speaking, it's not required to do this, but there are very good reasons to explicitly tell the memory you should read. Mostly because this takes a lot of time and it's expensive. We're going to tell the memory, hey, this is a load instruction, you need to read, and this is where you're going to read from, and then send back the value to me. So we get back the value from memory. It's a 32-bit value in our load word instruction. If we need to support other load instructions, load byte, load double, then we would get back different widths. If it was a load double, we need a 64-bit bus here to carry all of the bits at once, and then we would select which bits we want, or really which bytes we want. So we get this 32-bit value. That's our load value to put in a register. This is going back to the register file. That's great. Now, except for, can't do this, right? It's a problem. And the solution is a multiplexer. This is a mux. It's going to get a control signal. We'll call it mem to reg. So if mem to reg is 1, we send memory to the register file. If mem to reg is 0, we send whatever this thing is, the output of the ALU, to the register file. Whether or not we actually put that value into the register file still depends on the read-write signal. If read-write is 0, it doesn't matter what we send there. So that's a load instruction. Load word instruction. Okay. We can do arithmetic, we can do logic, we can do load instructions. Ooh, our computer has a little problem. It can only execute one instruction. The program counter is not changing. It's just going to keep executing the same instruction, whatever that program counter value is. What do we need to do with the program counter to execute the next instruction? Increment it, depending on what the size of the instruction is. Now, in our processor, all of our instructions are going to be 4 bytes long. Some instruction sets have variable width instructions, in which case you have to use some control logic to figure out how much you increment it by. We don't need that. We can do something very simple and stupid. I don't know if it's stupid, it's smart. Simple usually is smart. I don't know why they say simple and stupid. The number 4 into a simplified ALU, which is really just an adder. Okay, so the adder can add the value of the PC to 4. That gives us PC plus 4. And we put that into the input port of the PC. So that when the clock ticks, this will change to PC plus 4. And then that'll come out here. And then we'll get a new instruction. And then we'll do all this stuff with it. And eventually we'll write its result back somewhere, either the register file or the memory. The length of this clock cycle has to be long enough for all of these signals to propagate through, which is really long enough for the longest path through this circuitry, whatever that may be. For our processor, that's a load instruction because it has to hit all of these pieces. Means it's going to take the longest. All of the electricity is flowing everywhere at the same time, all the time. Right? It's pushing down the path, and whenever there's a change, it propagates through at different speeds, depending on how many circuit elements are in its way. Every time the electricity hits a circuit element, it takes some time to get through that. That's just physics. Change the PC, things start flowing, and they flow this way. We actually know the program counter of the next instruction long before we're going to change this program counter. Corollary, much of this processor is idle much of the time. So we can execute sequential instructions of a program, and we can deal with those instructions if they're adds or arithmetic or logic or load or store instructions. Anything else we need to write programs? Jumps and branches in order to implement iteration structures, conditional blocks, and procedures. I'm going to deal with branches. Jumps are a non-trivial but not too difficult extension of what we deal with for branches. So branch instruction, specifically, I'm just going to talk about branch equal and branch. Actually, I'm just going to do branch equal today. Compares two registers, register 1, register 2, RS, RT, and the label. We talked about the branch instruction encoding. So we know the RS and the RT, they're there for the branch instruction. The label is some kind of mind-bendy stuff. The immediate gets carved up into, I think the immediate gets carved up into pieces, and I can't remember for the life of me what the pieces are. But it doesn't really matter. It doesn't really matter if I remember it, because the immediate generation is going to deal with it for us. So whatever that process was to encode the branch label, the branch target, into the instruction, we will get out of the immediate generation the signed offset from the program counter. Signed offset of bytes divided by 2 from the program counter. That's what the label gets turned into in our instruction encoding. Our immediate generation is going to deal with figuring out what that was and sign extending it. So out of here, for a branch instruction, the immediate coming out of here is our signed offset of bytes divided by 2 from the program counter. In order to figure out what the address of that label is, we now have to multiply that number by 2 and add it to the program counter. And that'll give us the address of the branch target, because that's the inverse operations of how we constructed the encoding. So the decoding of the encoded immediate for the branch instruction is generate the immediate, multiply it by 2, and add it to the program counter. I'll do that up here. Let me see, I'm getting close to the edge of what I can see on the screen. Let me tilt this up a little. Haha, there we go. Now I can see everything. Should have done that a while ago. That's okay. I was just missing this little strip here, I think. So I got the immediate right here. I forgot to tell you it's 32 bits, by the way, coming out of here. So we're going to send this thing further, try to keep my lines kind of clean. Okay, so we've got our immediate here. This is just our immediate. Our sign extended immediate. Now we got to multiply it by 2. We put that into a shift left unit, just shifts by 1 bit. Now this is actually even simpler than it looks like, because you just take those wires and you add another wire with a 0 signal. Shift it. This gets rid of the most significant bit of the immediate. That's a multiply by 2. And now we got to add that to the program counter. Now here's the program counter. Let's send it this way. Wow. Into something that can add it. Now we just need an adder. Just arithmetic, just addition. It's not a full ALU. It's again just an add unit. Better teacher evaluations later about my handwriting. As big as I could make it and still have it on the video camera. Normally I would use the whole board. That's our branch target. Now, why didn't I use the ALU to do that addition? Well, I need the ALU for something else right now. I needed to compare RS and RT. Well, the values in RS and RT. Well, those values are here. That's RS, that's RT. Got those values, I can select that one. My control logic can tell me, okay, select the RT value and the RS value. Send it to the ALU and do something. What should I do to determine if 2 numbers are identical? What's the result of ANDing 2 numbers that are identical? The same number. It's not going to be a particularly useful result for me yet. XOR, what happens if I XOR 2 numbers that are identical? I get 0 back. I can also subtract. So either a subtraction or an XOR, it doesn't really matter. One of those 2 operations is going to be sent to the ALU. And the output is 0 if the numbers are the same, and it's not 0 if the numbers are different. My ALU is actually going to have an additional output, a 1-bit output, that's going to be true if the result of the ALU operation is 0. I'm going to add a 0 output of my ALU. When the 0 signal is true, the ALU result was 0. When the 0 signal is false, the ALU result was non-zero. To say it more confusingly, when 0 is 1, the ALU was 0, and when 0 is 0, the ALU was non-zero. Not intended to be useful. So the 0 result is going to help me to make a decision about whether or not to take the branch. For a branch equal instruction, I want to take the branch when the 0 signal is a 1. Is it 1? If it's a 1, I want to take the branch. If it's not a 1, I want to take program counter plus 4. I'm going to cheat here. I'm going to send my program counter plus 4 this way. I'm going to put a multiplexer here to select whether I'm going to take the branch target or the program counter plus 4. When the input to this mux is a 1, I want to take the branch target. When it's a 0, I'm going to take the program counter plus 4. And I'll send that. That, of course, goes here. I don't want to accidentally take the branch target on any ALU operation that ends in a 0. So I can't just wire this here. I need a control signal that tells me this is a branch instruction and the ALU result was 0. So I got a control signal here called the branch signal. If it's a branch, then that control signal is a 1. If the result of the 0, if the result of the ALU is 0, this is a 1. I AND them together, and that tells me the instruction is a branch and the 2 values are equal. Therefore, take the branch. Otherwise, don't. Otherwise, just take program counter plus 4. This is a basic sequential processor. This is the simplest processor you'll ever see. It's not realistic. We'll talk about its flaws, but it's useful as an instructional tool so that you can understand more complex, realistic processors. Have a great day. The book has more words if reading is your thing.